Welcome back. In this video, we're going to solve our first example problem using the definition of the equation for a plane. The example reads as follows. Find the equation for a plane that passes through the 3 points P0 with coordinates 2, -1, 3, Q with coordinates 1, 4, 0, and R with coordinates 0, -1, 5. As we start this problem, I always recommend visualizing what we expect to have. We expect that we're going to have 3 points in our plane. Here I'm going to do the best that I can to represent a 3-dimensional object or surface in a 2-dimensional piece of paper. So we'll call this our desired plane in R3. And we saw in the problem statement that this plane should have 3 points on it. It should have the point P0, it should have the point Q, and it also should have the point R. One of the things that I checked was that these 3 points don't lie on the same line, and the way to check that is to see whether or not I can get from this point back to this point via a scalar multiple. And I can see really quickly that if I multiply 3 by 0, I get 0, but then these two would have to be zeroed out also, so these two are not collinear. And the same thing is true with these two. These are not collinear. And then finally, we can check the same thing with those 2 points. So indeed, we have this kind of triangular pattern with our points in our plane. When we are trying to solve this problem, we want to get an equation for this plane. And what we recognize is that what we have is these 2 vectors that sit in our plane that are in different directions. So perhaps we call this vector x and we call this vector y. And we say that x is the vector that goes from the point P0 to the point Q. And of course, we could actually calculate this based on the coordinates that we were given to begin with. So this would be 1 minus 2, and then of course this is 4 minus a -1, which would be 4 plus 1, and then this is 0 minus 3. So here my vector x would be -1, 5, -3, and that's just by doing a little bit of work there. And the same thing when we look at y, we'll say that y is the vector P0 to R, starting at P0 going to R, and given the coordinates up here, we see that this would be something like 0 minus 2, -1 minus a -1, which is of course plus 1, and then this would be 5 minus 3, and this ends up to look something like my vector y is given by -2, 0, +2. Remember that when we are solving for the points on a plane, we want to find a specific point on the plane, P0 with coordinates x0, y0, z0, and then a normal vector to the plane, which we called a, b, c. In this case, any general point satisfies the dot product equation for the plane, which is the normal vector would be orthogonal to the vector connecting our specific point to the general point. And by orthogonal, we mean that the dot product is 0. The optimal picture that I like to keep in my mind when I'm thinking about this is the plane is the set of all points P0, such that when I draw a vector from the set of all points P, such that when I draw a vector from P0 to P, that vector sitting in the plane, which we called x in this case, is directly orthogonal to the entire normal direction defined by n. And that's what this equation said. Well, we actually have, in this case, in this specific problem, we have P0 is equal to, P0 is given by 2, -1, 3. We do not have n. However, if we look back up into this diagram, we know that the vectors x and y both sit in our plane. Those are specific vectors that connect the exact points that are given in the problem statement. And the moment we know that we have x and y in the plane, we also know that we can use the cross product to generate a vector normal to each of these, which you might call n cross y. In other words, we can use the cross product to get the vector normal to the plane, and this is what is known as the direction of the plane. We'll talk more about that as we go on. To get n, we find the cross product of x and y. Of course, I want to boot up Mathematica and do my cross product using that software, but I think it's valuable to actually make sure that Mathematica doesn't have any bugs in its code, do it by hand, and then confirm it using the software. So here we go. We're going to write I, J, K in the first row of my 3x3 matrix. I'm going to write the specific entries of x that I calculated in the previous screen in the second row, and then the specific entries of y in the third row. We have this little determinant trick that we use, which is to write a copy of the columns 1 and 2 outside. And then we look at the downward diagonals as positively signed. And this has to do with the sign of the permutations that these correlate with. That's well beyond the scope of Math1C. You could get a really fun description of this in the linear algebra class that I teach at Foothill College. Yay, linear algebra. I'm so excited. Here we go. Here we would have 10i minus, well, it becomes a plus actually, 6j plus 0k. And then let's go downwards. This would be minus 10k. Next one would be minus 0i. It doesn't matter plus or minus. It looks like it's going to be plus if you do two of them, but it's 0, so that doesn't matter. And then it looks like this would be minus 2j. When we combine all those together, we would get a normal vector that looked like 10i plus 4j minus 10k. And of course, this would be written in component form as 10, 4, negative 10. Once we have this, we could actually go back to the definition of our, did I do something wrong? Of course I did something wrong. Look, 2 times negative 1 times negative becomes a positive, which means this is 8. Silly Jeff. Tricks are for kids. I have worked about a 16-hour day today, so you have to forgive me for that. But there's no excuse, I agree. And of course, I'd say the same thing here. Negative times a negative becomes a positive. Oh, God. Look at those rookie moves. Okay, so anyways, we got this cross product. This is exactly why Mathematica would be helpful for tired, blurry minds. Now that we have the normal vector, we can look back at the dot product equation of the plane, which looked something like this. Okay, so now we would go, this would be 10, 8, 10, and then I would dot it with x minus, well, what was the first coordinate of P? I think it was 2. The second coordinate of P naught was a negative 1, so this would be a positive 1 because minus is a plus. And then the third coordinate was 3. And we said that the plane is the set of all general points such that this vector is orthogonal to n. So we can actually do this calculation out. This becomes 10 outside of x minus 2 plus 8 outside of y plus 1 plus 10 outside of z minus 3, and this is equal to 0. And then we can start to do some algebra, which we're quite good at this point in our lives. So this would be minus 20 plus 8y plus 8 plus 10z minus 30 equals 0. And of course, we can go ahead and collect the operative vectors here and then bring all these together. So minus 20 minus 30 would be what? Minus 50. Plus 8 is minus 42. I bring it over to the side, and this is plus 42. And what's really fun about this is that all of these scalars are divisible by 2, which means I can simplify by dividing by 2. And then notice something else. If we looked at this normal vector, which we might call n1, the normal vector has components that are given by the coefficients in front of the actual scalars here. This would be 5, 4, 5. And in this simplified equation, notice that this is exactly 1/2 times 10, 8, 10. 10, 8, 10 was the original normal vector that came from crossing. And this goes to the whole idea that what matters is the direction of the normal vector. That's what defines the plane. So we call the direction of the normal vector to the plane is the direction of the plane. And in this case, you have to remember that the direction of the normal vector is given by the set of all scalars multiplied by the normal, where the scalars run through the entire real numbers. And that's what you see here. You could have easily used a simplified version of the cross product, which would be to just factor out a 2 from the original cross product, and you'd get the same equation out, which is pretty freaking cool, I think. Same equation, meaning to say that you'd get the same points when you solve these, which is quite amazing because the 2's factor out of both sides. This is exactly what we were asked to do. Let's confirm that this equation for the plane actually contains the 3 points that we started with and the vectors that we made from those points using Mathematica. Switching over, here we go. Here we are in Mathematica. Before we begin, let's go ahead and save this into the appropriate space. We'll call it Lesson 6 Examples. We wanted to confirm that our intuition, that the equation for the plane that we generated in our paper and pencil analysis was actually the plane that we wanted. To do so, let's go ahead and open the Basic Math Assistant. This will give us all our options here. So I'll begin by defining P naught, which is the first vector. Here I'll go ahead and write that the entries of P naught were 2, -1, 3. I'll go ahead and suppress this output. And then we had the vector Q, which I'm writing in all lower cases because these are user-defined variables. Anything that with a capital usually is reserved for, I like to reserve for Mathematica commands. This makes it so that there's no confusion between native Mathematica commands and the ones that I make. So here we have the 3 vectors, P naught, Q, and R. We saw from the last part of this video that we were going to use the contour plot 3D command. Let's open and close brackets immediately. We'll go ahead and call this the end of contour plot 3D. We saw that the equation for our plane was given by 5x plus 4y plus 5z equal to 21. We could, of course, bring the 21 over to the other side and keep it in the general form that we talked about in the first videos of Lesson 6. In the contour plot 3D, we need to tell Mathematica what the x values range from. So in this case, maybe we'll say from -8 to 8. We'll do the same thing for the y values. So we'll say that y's range from -8 to 8. And then, of course, we'll say the same thing for the z values just to make it a nice square, or box-shaped. So here we have the plane that we were looking for. We are not yet sure that our points lie in this plane. In order to confirm that, I'm going to do some changes to this. So we'll say contour style let's do directive. This allows me to change the color. So we'll go blue. And then of course, this is not going to be see-through, which kind of bothers me in some sense. So what I'll do is I'll introduce a gradation on opacity. We'll go 0.2. So now I can see through that plane. Right now, Mathematica is automatically turning on the mesh. I would like to turn off the mesh, so I said please make that false. And then perhaps we would like to put the origin right through the 0, 0, 0 point. So now we have the entire plane situated here. And then perhaps we also would like to label, so we'll say axis label, and we're going to label these x, y, z. So there's my x, y, and z components. Let's see if we can see them. Here's x, here's y, and here's z. Not super clear. Let's go ahead and turn off axis origin to make sure that the x, y, and z, yeah, there we go. That's a little bit better, right? So here's the x, y, and z. Okay, so we've now just plotted the plane. We're going to go ahead and combine the plot for the plane with graphics. So we're going to use the show command as we have seen in the past. Show allows us to combine many graphics together. Here we'll go ahead and do graphics. And this would be a 3D because it's going to be in 3D. Open and close dots. So we'll go ahead and do point size. We said that the point size that we were looking for was like 0.02, I believe. And then we're going to go ahead and graph the point P naught. Okay, let's go ahead and look at that. Okay, so indeed we see that that point lies in the plane. Let's go ahead and do this for all 3 points. And perhaps if we don't want to be redundant, we'll go ahead and write R and Q. Okay, so indeed we've just confirmed that all 3 points are in our plane. To do this, I'm just clicking and rotating. Okay. We also defined vectors that go from P naught to R and P naught to Q. I'm going to go ahead and do graph these vectors using the arrow command as a graphic. So I just copied and pasted the last graphics. And then this is going to be arrow rather than point. And the first arrow will go from P naught to R. Okay, that's a little bit too thick. So let's go ahead and go 0.8. Okay, so there's the first arrow that I have. And the second arrow will go from P naught to Q. So I'm going to go ahead and copy and paste. Okay, let's go ahead and confirm. Yep, okay, so we have the 3 points that we started with are all in our plane. The 2 arrows that connect those points are indeed in our plane. And now we maybe want to visualize the normal vector. So here we said that the normal vector was going to be equal to 5, 4, 5. And then we're going to go ahead and introduce a dummy variable. Maybe we call it D. And D is going to start at P naught, P naught, and go to the end of 5. Okay, the end of n. And what's really interesting about this is now I can actually graph an arrow, and let's graph this arrow in red, and this arrow will go from P naught to D. And the reason I wanted to do that is notice that that arrow gives me the orthogonal vector to that plane, which comes from the cross product. Right? So that gives me the plane that I wanted to define. And look at this. If I kind of zoom so that it's, yeah, do you see that? That the plane is the set of all points that are orthogonal to my normal vector. The last thing I wanted to show you was we could confirm using Mathematica that the cross product of these 2 vectors that we had defined was indeed what we expected. So I think we called x the vector from P naught to Q. So here we would write x as this vector, and then, oh, sorry, y was the vector from R to Q, if I remember correctly, right? r to p naught, excuse me. So here we go, p naught. Oh, and it's complaining. To do the automatic subscript, I'm using control underscore. You could do the same thing by writing p, highlighting it, go up to this, let's see. Oh, go down, here we go. Do you see this on this basic math assistant? I go the underscore there, and then there's not. Okay, so now what I'm gonna do is I'm gonna go ahead and take the cross product using the cross command of x and y, and I won't suppress, so I'm not going to put a parentheses, or excuse me, a semicolon there. Here is my cross product, which is the exact cross product that we got via hand calculation, and then there's the graphic. Kind of cool, right? In the next video, we will continue our discussion of examples of how to generate equations for plane. See you there.